So thank you very much for coming. I'm Arno. I'm from ThinkCell, and we are a small software company actually here in Berlin. And I will talk today about a small part of our library that deals with text formatting. And of course, as you know, text formatting is everywhere. Everyone is talking about text formatting. Everyone has a different approach. Everyone has a different idea. And I'm sure you know the XKCD comic that says, well, we're just going to invent yet another standard for text formatting. And of course, that one is going to be much better than all the other ones. So let's talk about first, what is text formatting? You have components of text, little snippets, and you have a certain order that you want to put these components into. And then maybe per component, you have some parameters. You have a number, and you have certain description of how you want to format this number. And you put this all together, and at the end, you have a string. That's, in a nutshell, what text formatting is doing. Now, there are essentially two ways to describe how to do the formatting. One way is the format string. You supply some string which has some embedded symbols, like printf, or the AppStar library. Google is doing it the same way, or also the format library that may make it into the next standard, or make it not into the next one, but maybe someone. I'm not sure what the state is. They are actually supplying format strings, and these symbols are being replaced then with components that you supply along with that format string. The other option is that you use what I call just C++. You put together C++ constructs in some way. For example, IO streams uses the shift operator, or you simply concatenate strings, and that describes how you want to put together your string. We can go through each one of them and see which one is good, what are the pros and what are the cons. So let's look at format strings first. What is good about format strings? You could argue format strings give you a better idea in advance when you write down the format string, how that string will eventually look like when you print it. That's good. Now, most format string libraries nowadays do compile time validation of the format string. But if you don't want to do that, or if you don't need that, then you can actually supply the format string at runtime. So you can calculate some format string. Not a use case that's terribly often, but terribly frequent, but you can do it with format strings much harder if you want to change around a C++ construct. Now, what are the downsides of format strings? First of all, when you supply the format string with the symbols, well, these symbols, by necessity, somehow interfere with the content of the format string. So there are some escaping rules that you have to obey, and you have to remember to do them. Otherwise, you get the wrong format. In a way, also, the format strings supply a second language over C++ to describe what you want to do with your components. So the percent writing of printfs is completely a different language from C++. It doesn't look anything like it. And it begs a little bit the question, we already have a language which is C++, so why do you invent another one? It also gives us the problem that when we want to supply snippets which are not necessarily the ones that the library already knows about, that you have some custom components in your string that you want to format, every formatter of these custom components needs to bring a little parser, hopefully compile time, maybe not, that actually understands the little language that you write into your string and turns it into a description of how you want to format your strings, or your components. Now, this is what I dislike the most about format strings. There is no gradual change in syntax from simple concatenation of strings to actually inserting something that's more complicated than simple strings. When you just concatenate strings, it's all already in string form, then you probably just want to write down the strings. You just put them together. You don't want to write a format string for it just to concatenate a string. Now, you come along and now you say, oh, I need a number in the middle. So in order to put that number in the middle, you have to now jump to the format string notation. You have to write %, %s, and then %d, and then %s. You have to make up that format string. in order to switch from going from concatenating strings to doing formatting. And of course, the danger with these kind of mode switches is always people are reluctant to do them. So you have code that just concatenating strings, and now someone wants to put together or wants to insert a number. Well, it's much easier just to locally just fudge something where you have a format string as just a %d, and you're just going to generate a string and insert the string there somewhere. And then someone else has to go and clean up the code and say, oh, no, you should really use a format string for it. So that's kind of ugly. Now, there's one area where you really need format strings, and that's internationalization. Usually, you don't do your translations in-house. You usually give it away to some agency because either you don't have a Portuguese programmer, or the Portuguese programmer has other things to do than translating your program. So you go to a Portuguese translation agency and give them the strings in your program and ask for the translated strings back. And to do that, you usually use some sort of format like XLIF. That's the kind of the industry standard. It's an XML format, and of course you have to supply strings. You can't supply C++ to them and ask them to rewrite your C++. And of course, the text may contain placeholders, like this one. So in this case, you really have to use format strings. There's just no way out. But you only want to, this is an outside agency. You are dealing with someone you don't know very well, and they may do a good job or not such a good job. You don't really know. So you only want to give them as much control as you absolutely have to. And there are certain things that they must be able to change. In particular, the order of components that may change between languages, that they turn things around. But other things you probably don't want them to control. So, for example, whether to use a comma or a decimal, or a comma or a point as a decimal separator, is probably something you can pull from the operating system or from some library, from some database that is dependent on the region. Date formats. You have one language you probably are going to translate to American English, but then you're going to run the program in England. And there, they expect the dates not to be in month, day, year, but in day, month, year. They swap the first components around. So you want to do that how it is configured in the operating system, not how the translation agency decides to do it. So that's a good point why you really only want positional arguments in the format string. For us, it did a good job. We are doing lots of translations into all kinds of languages, and for us, doing it with just positional arguments was enough. Yeah, I also have decimal places. I mean, if you're printing yen, then you want no decimal place, and if you print dollars, you want 2 decimal places. But that's not depending on the language. That depends on your currency that you're dealing with. So that's not something that you want the translation agency to decide either. Now, let's go to the just C++ side. The first thing that comes into mind are the good old I/O streams that come with C++. Of course, everyone despises them. They really abuse operator overloading. They do this funky overloading of the shift operator. They are excused because they didn't have variadic templates, so that's okay. They have other sins as well, other sins besides this one. One is that they use these stateful manipulators. Into your stream, you put these magic things like std set precision, and then your stream changes the way it formats numbers. That's particularly impractical if you're passing your stream around the program and everyone prints a little bit, because then it's always a big surprise. What am I going to, if I'm getting a stream, what's that state of the stream? How is it going to print my next number? So I either have to reset the whole state, which is inefficient, or I have to somehow have a really good convention and code reviews of what state that stream is. We've been there. It's a nightmare. Some of them also work for the whole rest of the stream. Some only apply to the next argument. So you have to know which one's which. So it's tricky. And they're also slow, in addition, because they have virtual callbacks. They connect the I/O buffers with the actual stream using virtual calls, and that's not particularly fast. And to end, when you actually want to get the string out, you have to make an additional copy of the whole thing. So it's particularly bad. The other option is to just concatenate strings. So now there you also abuse overloads, operator overloads a little bit with the plus operator this time. You have no formatting options from the standard library to start with. You really just have this std2 string, which gives you very simple text formatting. I think they're little used. And they're also slow because it generates many temporaries, right? Every one of these, if you write to string, it will generate a string, and then you concatenate the string, and it'll generate another string and throw away the old one, and so you're going to generate many temporaries, and that's not going to be very fast. But I like this. I like the syntax. I like it because it's kind of the essence of string formatting. It goes gradually from concatenating strings to formatting. So I like the syntax. It's very easily extensible. You simply write a function. If you want to print something special, you write a function that returns the snippet you want to print. And the only real problem is that it's slow. But I think we can overcome that with ranges, and this talk will show you how. Now, first of all, a few questions about ranges. Who knows the range-based for loop? All the hands go up. Not all of them. Who knows that the C++ 20 ranges? They have been just voted into the standard. We are going to get ranges in the C++ 20. And there is an extension, the range v3 library. That's where really the C++ 20 standardization came out of. That's Eric Niebler's range v3 library. Anyone familiar? Yep, a few. Okay. Anyway, who already uses ranges in everyday programming? Who's writing code with ranges all the time? You must. Okay? I'm not going to ask what you're using, but use ranges. It'll change the way you program forever. Okay, use range v3, use our library, just use something, because it will really make your life easier. We adopted them early on, and the whole code is full of them. It really makes your life a whole lot easier. All right, so here's the essence of ranges. Instead of putting your iterators everywhere, usually you write stit find with iterator begin and iterator end. You can now put together these two iterators into one object called a range, and then you write stit find with a single parameter range. Doesn't sound like much. For C++ 20, range is anything with a begin and end, so you can plug in the containers. You can plug in. They have spans, which are ranges delineated by pointers. So they have a little bit of range functionality, but still quite limited. The big stuff is in the range v3. As I said, yeah, ranges can own the elements. That can be the containers, or they can also just reference the elements, like stitspan does. It gets interesting with ranges that do actually lazy calculations. So when you're writing an expression like this in our library, TC filter of range and a predicate, it will actually only capture into an object the range and a predicate, and it will still not perform any actual work. And only when you start iterating, it will actually start skipping the elements that don't satisfy your predicate. Now, why do I think I know something about ranges? We have an in-house range library. It's evolved from Boost Range. It's under Boost license. We have it on GitHub. So at the end, I'll show you the link if you want to use it. We have about 1 million lines of production code that uses that library. And normally, you have that chicken and egg problem of library development. So you only know how to write a good library if you have lots of code that uses that library. But if you have lots of code that uses your library, you can't change your library anymore, because everyone is going to scream when you change the library. So what do? Well, we actually have all the code, the 1 million lines, in-house. So we have resources, actually people, that do the refactoring when something changes in the library. So we actually have the freedom to change, to try things out, to implement a library, to implement a concept, and change it again when it doesn't prove to be the best that we can do. And we've been doing this now for years. And this is how slowly the library evolves and gets better. That's why I think our library is pretty good, because it's seen a lot of usage, and we had the freedom to change it at any time. Now, this is the effect that you would have. What I'm suggesting is use range algorithms, range methodology for texts everywhere. Don't use the member function of basic string anymore. Just throw them away. So instead of string find, getting an index back, you would work with iterators and stit find. What are the advantages? The same generic algorithms you use for other things will also apply to your string. You will only have to use one set of functions. You are pretty flexible with string types. You don't have to commit to a particular string type. Not everything has to be a basic string, because you are free to implement range wrappers around any sort of OS-provided strings, of anything that your library wants. You just put it into a range wrapper and just use your range functions with these strings as well. So you have uniform treatment throughout. Unfortunately, C++ 17 gave us basic string view. That's not so bad. But basic string view actually perpetuates the whole member interface of basic string. Of course, that was by design. Basic string view is meant to be a drop-in replacement for basic string. But it comes with a caveat. I would say basic string is fine. Just all that member function stuff, just don't use it. Don't go there. Go to ranges, and you'll be much more future-proof. Now, we can use the ranges for text formatting. All the range libraries already have concatenation, string concatenation, or range concatenation. This is our TC concat, concatenates the two strings. There's a similar syntax in range v3 that every range library has some sort of concatenation. Now, to format data, we simply add some formatting functions. Here is a simple sdec where you write, well, you have the number you want to format and say the number of decimal digits, and you just insert that into your set of ranges that you want to concatenate. And this sdec is a range like every other range. Keep in mind, this is not like IOStream. IOStream lets you insert the data that you want to format, the data type, into the stream. We don't do that here. We actually convert it first into some sort of string, conceptually, and then we insert it into the longer string. And then we don't need a format function. It's not special anymore. It goes gradually from we are just concatenating strings to I want to format something, so I drop in my formatting function. Extensibility, again, is trivial. Any function that returns a range is basically a customized formatter. And you can return things like here with a concat. You can just say, OK, I call my sdec and append my dollars. And if I need this everywhere, then I just put that into a function, and I can use it as part of my other ranges. All the range algorithms work. So the sdec, you can do it for each over the sdec. That's OK. It's a range. It will spit out the characters that would otherwise print. You can use the range algorithms on concat. That's all fine. You can filter it. You can do whatever you like. Now, at the end, at some point, you want these strings to end up in a container, like a basic string. How do we do that? Well, strings offer empty construction. Well, you just the default constructor just constructs an empty string. And you can also construct a string already from a single other string. Right now, this other string is either string literal or already a basic string. Well, maybe we should add just arbitrary ranges that we can generate a string from. So I suggest allowing a construction like that one, either from a single argument, as here, you can put in an sdec or a tc concat, or we can also add n ranges at the same time, because I don't really know. I mean, it seems natural if you can have one parameter and makes a string out of them. If you have n parameters, why not concatenate these n parameters? If you don't like it, don't use it. It's essentially syntactic sugar. Oh, but we have already string constructors that take multiple arguments. So if I'm suggesting to basically concatenate strings when you supply multiple arguments, what do we do with these? I mean, these are all valuable constructors. We can't just throw them away. Let's see what they are doing. The first one is actually undefined behavior. It takes 3 elements out of A, but A has only 2, because A and the null terminator. That wasn't what I really wanted to do. Let's try something else. Let's try. OK, this adds 65 times Control-C, which you can clearly see from how it's written, that it will add 65 times Control-C to my string. That's very useful. Well, and finally, OK, this one adds 3 times the A. So I would say, let's deprecate this stuff. I mean, this is unreadable. You can simply write that. You can simply say what you want, and then you just assign that to a string. So you just describe the range, and then you make the string out of it. Since we cannot arbitrarily go around in a standard library and patch stuff that we don't want, we just came up in the library with explicit cast. Explicit cast is kind of the constructor that we would like to have, but that we don't have. And so in this case, in our library, this works. You say explicit cast with std string, and it's variadic. It'll just pass the number of arguments to that virtual constructor of std string, that desired constructor of std string, and generate the right string from it. Now, there's also a wrapper for mplaceback that also uses explicit cast. So you can do something like that. If I have a vector of string, and then I say, okay, cont mplaceback vector and a string-like thing that I can create a string out of, like the sdec, then it will automatically turn the sdec, when you mplaceback it, it will automatically turn it into a string and put it at the end of the vector. Explicit cast in the library is not restricted to containers, but I'm showing you here the container part. Of course, you can also append, right? That's pretty basic. You have your container in the front, and then you have your variadic set of arguments in the back. Again, there is a one argument form, but you can also, as a syntactic sugar, have the variadic form. And I promised you placeholders. So if you need placeholders for translation, certainly, you can write something like that. You can say, okay, placeholders, TC placeholders, and you can embed that. The TC placeholders will just output a range again. It won't actually print anything. It'll just be a range. And the arguments that you put at the very end here that's a range as well. And it'll just insert that range in the right place into your string that you gave as a format string. You also have named arguments. So if you don't like to write 0 and 1, maybe that's if some other people have to edit this format string, they may not understand what 0 and 1 means. So you can actually give them proper names and then use named arguments. Okay, so that's basically the syntax. And if we just implement this naively, then each of these formatters, like a sdec, would simply return a string. And then the concat returns a string after concatenating all the strings, and the append just appends strings. And then everything would be very simple. But again, it would be slow because we would need to allocate all these strings and copy them around, and that's what we didn't want to do. And also the talk would be over. So since we still have a little bit of time, let's talk about how we implement this thing efficiently. All right. So the first thing that we want to do is when we concatenate all these strings, we would have to do a heap allocation, at least for longer strings. If they surpass the small string optimization, we would need to actually allocate memory. And we certainly don't want to allocate memory while we are just putting together this string object, this range object. So what we will do is we will generate the actual character sequences during the iteration, during the time when we actually traverse the range. We make a lazy range. And then the size of these formatter objects is actually going to be constant. It's going to be known at compile time. And then we don't need to allocate any memory. So how does this look in practice? When you have a function like my dollars here, then the sdec f2 will just capture the f and the 2 as actual members. And so that's known at compile time. It doesn't require any heap allocation. Same with the concat. It knows how big the sdec is and how big the dollars are and can put this again into one object. Again, no heap allocation. With these things that actually are storing, and that happens a lot here, we are capturing things into an object and to evaluate it later when we actually iterate. And this capturing happens, and this is different from range v3, there they allow L values, and they always capture these things by reference. We do the same thing for L values, we capture by reference. But if you give us an R value, then we actually copy the value. We move the value into the structure. So you don't have to worry about lifetime so much. Works very well in practice. You rarely have any problems where things go out of scope and you're like, oh, where's my object? At the end, what you're getting is something a little bit like expression templates. You basically get this tree of objects that describes all the components of your string. And these can get quite large. We have like basically whole websites, web pages described as one of these trees. And then at the very end, we'll traverse a tree and write it into a container or write it into your HTTP. And it will never actually be a string. It will directly be written to the HTTP output. Now, how do you do fast formatting into containers? We have now our tree of things, but we want to add it to a container. We want to create an actual string. The fastest possible way to do that, really, is in advance to determine the string length. Then you do one memory allocation, and then as quickly as possible, you just fill in the characters. Just at a pointer location, you just fill in the characters one by one. That's pretty much the fastest way I can come up with. So how do we do that? Well, our first attempt could look something like that. We take a range, and then we fill the container. We give it an iterator to the beginning of the range and an end of the range, and then that container will be filled with the content of the range. What could be easier? Well, the problem is these formatters are not random access. When you're printing, say, a double, it's not so clear from the get-go how many characters you are going to need. So this is not a random access range. You would also be able to have to jump to any particular character inside the range. You don't want to write that stuff. So in practice, these things are not going to be random access. Now, this has the effect that actually the string constructor will run twice over that range. It will first run over it to determine its length, then allocate the memory, and then run again to actually fill itself with the content of the range. That's the default behavior of the standard library. In order to do better than that, we allow the formatter to expose its size. So in practice, the size, determining the size, is not as costly as actually printing the strings. So you can make a quick and dirty determination, and actually the format library does it the same way. They do a quick determination how long it's going to be, and then when you actually do the formatting, it'll actually calculate the actual digits. So in order to make this work in general, the formatter is going to have a size member that just calculates the size up front. And then we will have to write an explicit loop because we can't use the container constructor, unfortunately, because it will run over this whole thing again. We have an explicit loop to actually fill the container. So we only run over our formatter once. This results in code like that. You do a cont and then you do a reserve. And it looks good until you discover, oh, there's also append. Okay, we have, yep, it's still append, looks the same way. You first reserve here, right, cont size. This time we have to take into account that there may be already something in that container. So we reserve the size plus the size that we want to append. And this looks good until you discover that reserve is evil. Reserve is the most horrible function I can imagine. Because reserve does what you tell it to do. If you tell it to allocate 5 characters, and it only has 4, it will allocate 5 and then copy the content. So if you have code that allocates always, or that appends always in a range of 1 character, and then appends another range of 1 character and another one, then it will just, the container will be expanded only by 1 element at a time. And every time you copy all the elements of the container. So you get quadratic running time. Been there, done that. So what do? Well, we have already so many wrappers, so I just add another wrapper that guarantees that reserve does reasonable stuff. That whenever you ask for reserve, it'll at least double or increase by a fixed factor. Golden rule is also something that is in the literature. It will just expand it by a constant factor, so you get linear running time when you fill stuff into the container, even if you do it 1 by 1 character. And then you use the cont reserve, and everything is good. Next bottleneck are actually the iterators. Why? Let's look at concat. We had lots of concats here. And the iterator inside a concat is effectively a variant over all the iterators of the components. So, because you may be in the first component when iterating through the concat, or you may be in the second one, or the third one, or the fourth one. So you have to have a variant of all these different iterators stored inside your concat iterator. And each time you actually either increment or dereference that iterator, it actually has to do a switch on which iterator am I. Am I the first component iterator? Then, okay, I'm the first component iterator. Let's increment. Let's check what I'm now reached the end of my first component. If I reach the end of my first component, I have to switch to the second iterator, or the iterator of the second component. If I'm already at the second iterator, okay, just do the increment here for a variant of 2 elements. Operator, the reference operator looks very similar. Again, you have to do a switch. Costs time. The stack is quite similar. There, you also, when you're iterating through your values, you have to keep track of where you are inside your iterator, and you have to kind of restore the state. Now, to see more clearly what is really happening, let's look at a more abstract level. What iterators are doing is external iteration. The consumer is sitting at the bottom of the stack. It's just running along. It has the luxury of a contiguous code path. And then whenever it needs a value, it jumps to the producer and says, hey, I need a value, operator star, operator plus plus, and gets the value. Now, that's great for the consumer because it has a contiguous code path. But for the producer, it's less than ideal. Because the producer, every time, it only has a contiguous code path for generating a single element. And then it returns that single element. And then it's called again and has to restore its state, which makes it harder to write that producer. You have to do more bookkeeping. It makes it less efficient. You cannot hold any amount of memory on the stack because your stack is essentially, or the amount of memory that you can carry from one invocation of operator star to the next invocation of operator star is limited by the amount of memory you have in your iterator. Or you have to go to the heap. It's different for the consumer because it's running at the bottom of the heap. It can just allocate any amount of stack memory at once. So you can turn the whole thing around. And internally, this is actually what the format library is also doing. So, and it happens that formatting text is just a lot more efficient with internal iteration. There, the producer is sitting at the bottom of the stack and is sticking their values into the consumer. Now, with text formatting, the consumer is very simple. It just adds stuff to the end of a container. It does the same thing every single time. But the producer is potentially doing complex things. So you are better off doing internal iteration. The problem is there is no internal iteration in ranges. So we have to edit. It turns out many range algorithms are actually okay with internal iteration. You can't write a binary search because you don't have iterators. You can't write a find as long as you insist on returning an iterator. If you only need the value, actually internal iteration is fine too. Many other things just work. For each works. Actually, for each is the quintessential is internal iteration. It will just give you every one element at a time. You can write an accumulate. You can write all of, none of, any of. All these things just work. I told you about these lazy algorithms that you can implement with ranges. They also work. The most important are filter and transform. They work. It's all good. We can write versions for internal iteration of these lazy algorithms. So let's extend the ranges to internal iteration. How do we do that? We decided that ranges, in addition to implementing begin and end, or maybe also instead of implementing begin and end, if they want to support internal iteration, they simply implement the function call operator. Why did we pick the function operator? The function call operator has the big advantage that you can write your ranges, if you write user-generated ranges somewhere in your code, as simple lambdas. So whenever you want to expose a range to the world, you simply return a lambda from a function. Usually capture this, and then you just write a lambda that sticks the values into whatever has been passed to your function. It looks like this. You have the visitor, this is the consumer. It gets the values. That's your regular body of the for each. But up here, this is the range. It actually gets a sink in the function call operator, and it will just stick whatever values it has into the function call operator, into the sink. So it gets a sink, sticks the values into them, and then returns. That's how we implement internal iteration. The std span operator parentheses is actually already taken, so we have to svina it out. Okay, that's fine. For them, actually, for anyone who cares to know, it's synonymous with a regular bracket, the square bracket operator for std span. And for each actually does the dispatching. For each internally it decides, does this thing support internal iteration? If it supports internal iteration, it uses internal iteration. Otherwise, it just writes a simple loop with iterators begin and end. Okay, how does concat now look like? Looks like this. Again, we have our function call operator that takes the sync. And we now iterate over all the ranges that we store. We store them in a tuple, in this case, and our for each supports tuples. So you essentially just write a for each over the tuple, and then for each of the ranges that are inside the tuple, you again call for each. So this nested for each actually is the internal iteration for the concat. And you can see there's no overhead. This is basically how you would write it if you write it by hand. If you would just iterate over the range, the first range first, and then over the second range, and then the third range. And this is exactly what the concat operator is doing. The concat wrapper or function is doing. Now, how do we use that in order to get efficient formatting? We need some sort of appender. We need a sync that we can stick into the for each down here that takes a single element and appends it to the vector or the container. Well, that's just an emplace back, right? So this is how our sync looks like. We have an appender. It takes a single value and forwards it into the emplace back. Easy enough. Now, I forgot about the reserve. So that's kind of critical, right? So if we just get the elements one by one, then we can't pre-allocate all our memory, which was critical for performance. So what do? The sync somehow needs to call size before it actually gets all the elements. And in order to do that, we said, okay, in addition to the function call operator, which the sync is getting all its elements passed into, we actually implement another customization, chunk. If your sync implements chunk, this signals to the for each. Before doing anything, just check whether this chunk will be compatible with the range that I'm having. If the chunk is willing to take that range, I give the range to chunk first. So, and then you can actually write the reserving appender that actually does the reserving up front like this. You implement a chunk that takes everything. So basically the for each gets taken its task out of its hands. It's like, okay, give me the whole range. Give it to me. Okay, thank you. You call the reserve by asking for the size. And so you've done the reserve, and then you call for each again. And in this case, you just cut off that reserving part from yourself. You just have an appender that doesn't do any reserving anymore because you know you've done already the reserving. So don't need to do that anymore. You may think, well, this chunk thing looks a little bit ugly because he invented some tool that is only useful for this reserving. Why would you do it's like a single trick pony? Not quite so much. If you, for example, have an appender that appends to files, and maybe you want to put your string into a file instead of into a string, you can actually write a chunk that takes contiguous pointer ranges. And so anything that basically gives you pointers, gives you a contiguous chunk of memory. And you advertise that by implementing a suitable chunk. And for each is going to check, can I pass this range into there? And if that range is actually a basic string, say, it'll say, yep, works. I can get pointers out of that basic string. And so the chunk will take the basic string and write it into the file in one chunk. So you'll gain efficiency. Now, if that doesn't work, then you are stuck with your regular operator, your function call operator, where you take the characters, the elements one by one, and pass them, in this case, to the chunk function to write into the file. So that's pretty much it. Now we want to know, how fast are we? How good is this? To benchmark it, I looked at a trivial formatting task because I didn't want to benchmark the formatter. I didn't want to benchmark how quickly I can come up with the digits for a double. Other people can do this much better than I can. But I wanted to know how much does the infrastructure take away? All the scaffolding that I put up, how much does that cost? And so what I did is our trivial formatting task is just format 10 times an A, 10 times a B, and 10 times a C. That's all I want to output. And I'm not going to, I'm basically have that repeat n is going to be what we're going to test because it's so simple. And then when you have something where the formatter does very little work, it should expose any inefficiency in the framework because that's where the time is spent. It's going to be spent in this framework. So in the strawman is this thing, basically handwritten loops. In order for the compiler not to inline everything, I said, okay, I'll write a function where you pass in the character and the number of times you want that character to be printed, and internally you're just going to fill the buffer. And the buffer, in order to, they basically keep that as simple as possible, not have any overhead in there, is just a static array of memory. So what we are going to write is we're just going to write into a piece of memory, add a pointer, and increment the pointer. That's as efficient a buffer you can wish to have. So that's the strawman. That's how fast the fastest way to actually do formatting of that particular kind. Now, the alternative is going to be this when we want to do it with ranges. We have the same buffer, but we have an appender, and the appender that it exposes just does the same thing. Whenever you give it a character, it will just put the character at the end of the buffer and then increment the end pointer. So we'll just append to the buffer. And then we write our TC append like we want to write it. We want to append to the buffer and then 3 times the repeat n. So what do we get? Well, if the repeat n is actually iterator based, we actually use iterators, we have 50% overhead. If we, on the other hand, use internal iteration, have a version that of repeat n, the repeat n will do both, right? It will support iterators, but in addition, it will also support internal iteration. And the for each that is behind the append somewhere is going to check, do you support internal iteration? And the repeat n is going to say, yep, I do. Okay, then I'm going to use the internal iteration. And in that case, we only lose about 15%. So we are about 15%, I would claim, 15% above the theoretically best string formatting you can potentially write, which I think is pretty good. Again, this is worst case test, right? The actual work that we are doing, the buffer is as trivial as it can get. It doesn't do any work. The formatter doesn't do any work. So all this time is really wasted in our infrastructure that we are, our syntactic sugar that we want to apply. Okay, now there's another test I did. I created a toy basic string implementation, one that doesn't have any small buffer optimization. It just has a single, basically, it just stores everything in the heap, has 3 pointers, begin, end, and end of memory. And you, again, have a trivial formatting task. So the strawman in this case is just our simple I append stuff to a string. All right? I append my string and the 3 repeats. Now, this is the standard appender. I'll show it to you again. And in particular, the standard appender here does an n-place back. Now the question is, can we do better? Can we actually go beyond the performance of that n-place back? Well, I mean, once we've done the reserve, we know that our string has a certain size. We don't really need to check anymore whether, and n-place back does that, of course, whether we reach the end of our allocated memory. n-place back has to check each and every time. And so we change it, and we change the appender to just say, okay, when you run the for each, after you've just done the reserve, we just simply fill that stuff into the available memory. We just do pointer filling. And we don't check for anything like whether we reach the end. We don't need to. And the string was actually only 30 characters that we filled in, and we did include the heap allocation in this case. So in addition to all this filling, we also had to go through the heap and actually get the 30 bytes for our memory. And still, the custom appender actually in the latest Visual Studio actually saves 20%. So 20% of the time is just wasted checking for end in the n-place back. And we can actually do away with that when we actually pre-allocate the memory and then use the custom appender. Of course, this requires our own basic string implementation that we don't have yet. Unfortunately, this uninitialized buffer is not exposed by basic string or std vector. But as you can see, there's still optimization potential. You can do more with respect to performance. Now, right now, all the snippets that you have in a concat, for the concat to implement size, all the snippets have to support size. What if one doesn't support it? One's like, I don't know how large I'm going to be. Maybe you have a long string, but there's something that's something little that gets formatted and you don't really know how large it is. You could say, well, we could have a min size. We have I give you an indication of how at least how large I'm going to get. And then you can allocate that memory already. And if I'm getting larger, then you have to maybe reallocate once. But you don't have to reallocate many more times when you are growing a large buffer. When you are appending strings to a file, you can do something similar. Right now, the std file internally is buffered. It carries around a buffer of maybe 512 or 1024 bytes, and it will fill it. And when it's full, it will actually go to disk. If you directly call the operating system function, we've tried, you are much slower. That you can't really do that. You can't. These are too many switches into the kernel. But if you would know about that buffer and about the buffer size, you could also, in advance, say, well, my buffer still has 370 bytes left, and if you could tell me your maximum size you're ever going to be, and that's no more than 370 bytes, I can just also omit that end check and just fill the buffer blindly, and save the end check. So for that, you would need this customization point max size. So min size is useful, max size could also be useful. Someone told me that actually in D, it's implemented like that. They actually have an interval exposed as how many am I supposed to expect. So there's a minimum size and a maximum size, both exposed as an interval. That would be one good idea. Okay, I showed you how to do use the range syntax and the algorithms for text formatting. I highly advocate to do that. If you want to do this with high performance, you need a few more customization points. You need internal iteration for ranges. Then you need this appender customization point for containers. And then the appenders also have to implement the chunk in order to do the memory pre-allocation. But if you all do all that, then the performance that you're getting is actually competitive with handwritten code. You can get our library on GitHub. There's the address. And it's now under Boost license. And if you want to help developing the library, you can go to www.thingscell.com developers and send us an application. Thank you very much for listening. I think we have time for some questions.
So thanks a lot for your talk. It was very insightful. And I do have a question regarding encoding. So do I assume correctly that your library only sees a string character-wise, not byte-wise? So for instance, if I have UTF-8, this may change. So I assume that handling the encoding, this would have to be accomplished by the iterators. Is this correctly?
Actually, so we of course have this problem with encoding everywhere, and we have our philosophy about how to deal with encoding. Our experience shows that encoding, some people think, okay, iterators are basically have to expose Unicode code points. So you have to some sort of iterator that spits out the code points that will actually decode your UTF-8 or UTF-16, whatever you have, and spit out code points. We found this to be largely unnecessary. Our philosophy is keep everything encoded as it is. Substring matching will still work. It'll still be okay. Concatenation will still work. In most scenarios, comparison, if you do some simple comparison, it will work. In most situations, you can stay in your native encoding. You can just stay in your UTF-8, UTF-16, whatever you have. We actually go one step further. Some people say, before string is entering my program, I have to go to a common encoding. I decide I'm going to implement everything with UTF-8. So whenever I'm getting something from the operating system, I'm just going to convert it to UTF-8. This is not a good idea. You have a lot of problems when, for example, Windows is great. It has file names, and these file names are character 16-bit value strings. It doesn't know about surrogates. It doesn't care. You can just plug anything in there, and it will make a file of that name. Now, if you insist on converting that to UTF-8, you're going to bail. This is not going to work, because this is not a valid UTF-16 encoding. And you are basically, if you insist on converting everything when it's entering your program, then you're really making yourself a lot of problems, more than necessary. What we do is we have a bunch of type defs in the program. It's cross-platform. It runs on Mac and on Windows. So they are not equal on all platforms, but there are basically some types like, okay, this is the character that I'm using for files. This is the character I'm using for the user interface. This is the character I'm using for XML. So you have a bunch of standard types that you have in the program, and only when you are basically standard worlds, you have, in most cases, when you're dealing with file names, you are not exposing these file names necessarily to the user interface. When you do, then you have to make a conversion. Then you have to actually take care of this problem. What are you going to do when you have invalid file names? In all the places where you are dealing with files, you just say, okay, I have to go to I have my program folder, and I have to go one folder up and then one folder down, and then I'm going to find my resources there somewhere to load them. I don't have to deal with that stuff. So we do conversions between UTF-8, 16 in some places, but we try to minimize them by keeping separate worlds of character encodings in the program. And this proved to work very well. We have very few problems with invalid encodings and things. You can be agnostic towards all this UTF-8 stuff. Another thing, if you're talking about encodings, that I recommend, when you're doing comparisons, in particular, what's quite frequent is case-insensitive comparisons. Now, they are a huge headache if you want to do them with Unicode, because it's very difficult to do this right. In many cases, in our program at least, in many cases, you are comparing against an ASCII string. So it's essentially just lower 127 code points in the lower ASCII range. And there, of course, it's trivial. So we actually have a function that only converts the ASCII characters to uppercase or to lowercase, and then does the comparison with whatever ASCII you want to compare with. It saves you a lot of headache coming up with some Unicode library that converts everything properly. It's much faster, much more efficient. Sometimes you can't do it. Sometimes you really need comparison. But even then, it's often very, very application specific. Like, how does Windows compare file names? It's case insensitive, yes, but it's not only case insensitive. It's a particular function you should use so that you are close to what Windows does. And what Windows does may not be the same thing as what Apple does, even though it's both case insensitive. So it becomes very custom, and putting that into a library and basically saying, okay, I'm going to standardize everything, didn't quite do our job very well. So that was the little detour on that.
Yeah, thanks for your little answer.
I just wanted to say that I think that your judgment that reserve is evil is totally wrong. I think reserving more than you want is totally evil. And if you need a custom strategy to allocate more, you should just call that in the function that calls reserve.
If you explain that to my developers and they all do it right, and they all understand it, and they, in particular, because it's not a local problem, right? You append a character somewhere, and then you go a completely different code path, and then you append another character. And if you expect people to see through all this and then do the right decision, then I agree with you. Apparently, the Clang developers of the standard library of Clang didn't think that. They are actually allocating more. Just the C++, the Visual Studio people didn't think so, and they allocate just as much as you specify. So the different implementations vary, and I think at least we need a standardized thing. They must be doing all the same thing, and I think the safe default is potentially to over-allocate, but opinions differ.
Well, it's a lot of waste if you do have things that potentially don't.
Yeah, if you do pushback on a vector, it's waste. I mean, if you don't pre-allocate, it's also waste because
and you can also
doubles.
skip the reserve if you just don't call the reserve. The vector already has an incremental strategy that provides linear time.
Not in our case, because I mean here the critical performance part here is that you know the size of the whole range at once, but you don't expose that whole range to the vector append. The vector gets appended only little snippets at a time. But we know from the framework, we know the total size of the range that we want to append in advance. That's the use case here. So if we had iterators that are random access, then it would not be an issue because the vector would do the right thing. But we don't have that. We have a internal iteration and we have a whole tree to traverse, and only we can actually know what the total size of that whole tree is.
But it doesn't matter. The thing is, if you don't call resize, the internal strategy of the resizing will just not always recopy your buffer. So you made the problem worse by calling reserve.
No, we can discuss it afterwards, but we are definitely faster if you do the right reserve up front. I mean, that's for sure.
If you do the wrong reserve, you may be faster.
Certainly not. Anything? Yeah, I think maybe a few minutes.
Hi, I have the question, is there any discussion about whether the internal iteration is going to be part of the standard?
Not that I know.
Okay.
And we putting stuff into the standard is a lot of work. I have a lot of respect for the people working on the C++ standard. So far we kept out of that to some. Don't get me wrong. I really have a lot of respect for the people, but it's a very bureaucratic and long process. And we rather and the library is also a work in progress. I wouldn't really know what to standardize because it's constantly changing. So it's hard to commit to like, okay, I'm done. And then 2 weeks later, a month later, you discover no, you're not done. You can actually do better. So that's kind of difficult.
Yeah, so thank you for the talk first. And so when you were talking about heap allocations, are you planning to update the library when this can happen at compile time as well?
Say it again.
Are you planning to update the library, or do you see potential for improvement when heap allocations can happen at compile time as well?
We don't really need compile time heap allocations. I guess if you had a compile time version of, say, a vector or something, and on the whole library would be const expr, which it could very well be, then you could basically use the same optimization you use for a regular vector at a compile time vector. And there are now efforts to put that into the standard, which are great. So it would simply work with these as well. We don't have any special effort. To construct these expression trees, you don't need any heap allocation. For putting it into a vector, you do. And there, it's basically just like any computation where you generate a constant vector. So if you had compile time const expr vectors, that would apply.
Thank you.
It's over. Thank you.